Any questions before we get started?
Can I have the syllabus, please?
I have a couple of them left. I did correct the syllabus and put it. I'm sorry.
I'll get one behind it. Two, actually.
I think this is all we have. All right, well, let's go ahead and get started with chapter 1. We're going to be talking about matter. Matter is defined as any substance that has mass. Mass, of course, is different than weight. Weight is mass as a result of gravity. Matter is basically composed of atoms. And we're going to talk a bit about atoms today. Atoms, elements, and whatever. Atoms are largely composed of protons, electrons, and neutrons. Protons are positively charged, electrons are negative, and neutrons are neutral. Protons and neutrons live in a place called the nucleus, little tiny thing. We'll see something about that later. And they're surrounded by electrons. Now, we all know what atoms are supposed to look like. Well, they don't look like this, do they? This is straight from Jimmy Neutron, or Big Bang, or something like that. This was a classic 50s representation of an atom. Nice big fat nucleus in the middle, and electrons in little orbits. Doesn't look like that, not really. In fact, quantum theory describes an atom much differently. The nucleus is a little wee tiny spot, 1 pixel worth, down in the middle here. The electrons are in a cloud surrounding it, not little orbits. The cloud basically reflects the probability of when or where you might find the electron somewhere within this region. This is for the element called helium. Helium has 2 protons, 2 neutrons in its nucleus, and 2 electrons out here. Atoms are very, very, very small. If this was a copper penny, it would contain roughly 28 sextillion atoms. Of course, this is not copper. Even a 1904 is only 90% copper. But nonetheless, this still contains lots and lots of atoms. Very, very small. Mass of a proton, remember the protons and neutrons are in the nucleus, is about 10 to the minus 24 grams. Now that's really small. That's the same number written out in decimal format. Now this other format here, this is referred to as scientific notation, and we will do problems and explain how to convert from decimal format to scientific notation and back again. We'll do those in just a little bit. Mass of, in this exponential or scientific notation, we've moved our decimal point 24 places over to here and shown that as our exponent. But again, we'll do that in more detail later. Neutron is very similar to that of a proton, and the electron is much, much less. Now, what that really means is that virtually all of the mass of an atom is tied up in this little tiny nucleus. If you have a substance, a piece of matter, that consists of only one type of atom, that's called an element. There are roughly 115, 116 elements known. Every element is given a chemical symbol. The symbol is quite often derived from the name, and that makes it easy. But there are some symbols that are based on ancient Latin or Greek. Iron, for example, is Fe. Chemists tend to arrange elements in what's called the periodic table. We'll actually do the periodic table in Chapter 2. These are just some elements. This is a starter list, if you will, of hydrogen, helium. You'll note that these guys are very simply based on the first letter or two of the name. Those are no problem. We also have these funny guys, sodium, iron, silver, gold, and lead, that again are based on the old names. Now, I'm often asked if you have to remember the names of all of these elements. And of course you do. Will I do something stupid like give you a periodic table and ask you to fill it in? No, of course not. That would be silly. You could just look it up, can't you? But there are lots of ways that people use to remember names of elements. This is a very large number. This is a very, very small number. In order to deal with these things, we're going to use what's known as scientific or exponential notation. Our 28 sextillion here is written this way in scientific notation. 2.8, that's our first two digits here. And then we have 22 zeros following it, and that's where the 10 to the 22nd comes from. If we wanted to express this number in scientific notation, again, we're going to move our decimal from here all the way to here, get this number, and then we just simply count how many spots we had to come over. Like we said, that was 24, and that's our number. So scientific notation really is not difficult to do. There are just some basic, simple rules. So we're going to look at some problems, do a tutorial or two on how to deal with scientific notation. Again, we're going to have, it's going to be expressed as a product of two numbers. N is some number between 1 and 10, and a power of 10. What you do is you want to move the decimal from wherever it is, either a real decimal or a perceived decimal. So it's between the first or after the first non-digit 0. Figure out how many decimal places you moved it. If it goes to the left, it's a positive exponent. To the right, it's a negative. It's actually very simple. Let's deal with 950,000. Step 1, we're going to move our perceived decimal point from here to here. And we're going to write 9.5. Next, we count and say, how many spaces did we move this over? Well, we moved it 5 decimal places, and we moved to the left. That makes it a positive exponent. So we simply put that in like this. Probably this is much simpler if we just do it. Why don't you take your little sheets and let's convert each of these guys into an appropriate number in scientific notation. While you do that, I tend to stand up here and pace and look uncomfortable. For our first number here, we have 0.0257. We want to move our decimal point from where it lives right here to in between the 2 and the 5. When we do that, we are moving it to the right 2 places. To The right, remember, is a negative exponent. So this is 2.57 times 10 to the minus 2. Our next one, we have 125.6. Real decimal point. We're going to move it from where it is to right here, in between the 1 and the 2. That's moving to the left 2 places. So it will be 1.256. Oops. The reverse doesn't work on this, so ignore that answer. 1.256 times 10 squared. The next one, I already gave away the answer, 93 million. We're going to move the perceived decimal point from where it is here, in between the 9 and the 3, and that is 6, 7 places. Negative 65,800. Again, where it doesn't matter if it's a negative number or not, we simply move it 1, 2, 3, 4 places, write our digits, and of course, it is still a negative number. And our last one, we're going to move the decimal point from where it is to in between the 2 and the 7. When we do that, we're moving it 1, 2, 3, 4, 5, 6 places, so that is 10 to the minus 6. Any questions? Really fairly simple. Let's do it backwards. When we go backwards, we're going to, of course, keep our same digits. We're just going to move our decimal. In this case, we're going to go to the right now, 2 places. So 2.57 times 10 squared is going to wind up simply as 257. 10 to the minus 7. So we're going to go this way, aren't we? As we go this way, we're going to have to move our decimal point 7 places, and that's going to make 6 zeros. So we want to rewrite this thing with 6 zeros. That doesn't include the one in front of the decimal. That one's just there. That one doesn't really count. But we're going to move 6 places over here. 9.3 times 10 to the minus 4. We're going to put 3 zeros in front, and of course another 0 in front of the decimal. Here we have 6.580000 times 10 to the 4th. We will see in a little while that this is an important problem to do with the significance of a measure. Basically, when you have a number written like this, all of these digits, all these zeros have to be shown when you do the conversion. So we're going to take and move 1, 2, 3, 4 places here, but we keep our zeros on the end. The zeros on the end are what are called significant figures. We'll do those in a little bit, and they reflect the accuracy of a measurement. And finally, 2.78 times 10 to the minus 1, going to move it one little spot right to here, and it's 0.278. Any questions? Well, when we had our little introduction in the lab room the other day, I pointed out chemistryonline.com, and I talked about tutorials. If you take a look, my gosh, there's a tutorial right here called Scientific and Decimal Notation. That's what we've just been doing. So on your sheet are some problems. Let's go ahead and do these the way they appear in the tutorial. This is what the page will look like when you click on it. you need to click New Problem, and when you do that, something will appear. Every time you do a problem, you will get a different sort of problem. What you're supposed to do here is to simply take this number and convert it from decimal here into scientific notation here. Well, okay, we're going to have 8.3 as our exponent, aren't we? So the first thing you would do is simply type in 8.3. Now, in order to get our exponent here, we had to move this 1, 2, 3, 4, 5, 6, 7 places. So that will be a 7. And by gosh, we got it right. Let's do another. And I'll hush. Here we are moving our decimal point to the right. We're going to have a negative exponent, aren't we? First thing we're going to do is rewrite our 4.6. And we simply had to move our decimal point 1, 2 places, so we enter -2. Here we have 7.1 times 10 to the minus 7. Go ahead and write that in decimal format. Obviously, we have a negative exponent, so we're going to have a string of zeros in front, aren't we? It's a -7, so we're going to move here and then put 6 zeros at our decimal point. And we got it right again. Let's do this again with 5.6 times 10 to the 7th. This is a positive exponent, so we're going to take our 6, write it out here, and then we're going to move our decimal point over 7 places. When we do that, we wind up with 56 million. Now, see this show answer button? If you push that button, let's say that you got it wrong somehow, but if you push the button anyway, you will get something that shows up here that will explain to you precisely how to do the problem and what the answer should be. That's a very nice little tutorial. There's another one that applies to this. Oh, I guess there's one more of these. All right, well, this is simple. We're going to write our 6.1 here, and we're moving as 1, 2, 3, 4, 5, 6 places. That's a -6. Now, mind you, there's stress involved in this because I have to do these in real time here, don't I? Right? I don't know all these answers. This is another tutorial that I'd like you to look at called exponents. Once we have numbers in scientific notation, quite often we're going to use these when we work problems. Okay, so we'll be multiplying and dividing them. The rules are actually very simple. When you are multiplying exponents, they simply add. When you are dividing exponents, they subtract. So step 1, you want to look at your exponents, either add or subtract. Then you look at this, 5 times 5, roughly 25. That's going to be another power of 10. So let's work the problem here. Multiplication, exponents add. We have -5 plus 5, that's 0. We're at 0. Now we look at the coefficients. We have 5 and 5. That's about multiplying this 28. So that gives us another power of 10, doesn't it? That's 2.8 times 10 to the first, this guy. Therefore, the final result, exponent only, is going to be this, and that's correct. So go ahead and try one on your own. 1.71 times 10 to the minus 13 divided by 4.11 times 10 to the minus 2. Sorry, that was one of my sons. I told you I had 4 of them. They can never figure out my teaching schedule either. All right, so we have 10 to the minus 13, 10 to the minus 4. We are going to subtract them. Minus 13 minus a minus 4 gives us a minus 9. That's where we're starting. Looking at our coefficients, we have 1.7 divided by 4.1. That's less than 1, isn't it? So because of that, we're going to have another negative exponent. So instead of 9, it's going to be 10. Type 10 in, minus 10, and we get the answer. When you do positive exponents, just put the number. Don't put a plus sign. It will say you're wrong. It's not that smart. One more. This is division, 10 to the 19 and 10 to the minus 10. Because it's division, we're going to subtract. So that's 19 minus a minus 10 gives us a total of 29. Our coefficients, we have 1.8 divided by 1 is still 1.8. I could do that. So our exponent here is 10 to the 29. Now, when you answer 5 of these guys correctly, as it says here, this will appear, I hope. There it comes. Email your instructor. That's me. Okay? Don't change this to whatever. Leave it as intro@Chemistry Online. This says your email. Don't put your email in there. Like I said, everybody has an unidentifiable email. Put your name in there as it appears on the roster. So I would just type in my name. And then I would hit the submit button. Now, when you do this, this shows up in a special little mailbox on my computer, and it tells me that you have completed this particular tutorial. You got 5 right. So like I said on Monday, here's the deal. Do that twice. So you have to work 10 problems, get them right. When you do that and submit it twice, I'll have your name twice there, won't I? You will get 5 points added directly to your exam total. Okay? Now this goes for every tutorial that we sign. So right now, I want you to do, or today, tomorrow, whatever, before Monday, I would like, or Tuesday, Wednesday, whatever, I would like you to do significant figures and exponents. That will give you a head start on your exams, 10 easy points. Yep, that's 10 points. By the end of the semester, using this, you can easily earn 100 points. That's good. All right. Now that we know how to do exponents and stuff, Gord, I'm teaching, okay? Now that we know how to do exponents and stuff, let's apply it to some simple measurements. In science, we tend to measure things using the metric system. Metric system is very simple. Unit of length is a meter. We use an abbreviation. M stands for meter. A centimeter is a very common thing. That's simply cm. Mass, the standard unit, is a kilogram. That's kg. We'll measure things also in grams. That's just the G. For volume, cubic meter is actually the standard. That's an odd measurement, to be honest. Cubic centimeter is what most people use as centimeter, and we use the exponent cubed to show it is a cubic centimeter. All right, so when you're going to do a measurement of some sort in the metric system, what you're going to do is include a little prefix here. All the prefix is shorthand for some scientific notation term. It's just shorthand for it. So, if we wanted to do a millimeter, that's 1/1000th of a meter. What we do is, we're measuring in meters, so that's the M here. And we have a milli, that's the shorthand for 10 to the minus 3. So millimeter is simply 1 times 10 to the minus 3, that's that first M, meter. Simple as it could be. The thing that commonly occurs in problems in the metric system, however, isn't just writing millimeters and micrometers and knowing what they are, but you'll be given a measurement in something, and you're going to have to convert it to another metric measurement. That's actually very easy to do if we're going to, by using a set of simple ratios. For example, if we wanted to convert millimeter and meter, we could write simple ratios that relate a meter, that's 1, and a millimeter, that's 10 to the minus 3. We could say 1 meter is the same as 1,000 millimeters. We could say 1 millimeter is the same as 10 to the minus 3 meters. That's the ratio we had on the previous slide. And we can flip these upside down. Why can you flip it upside down legally? Because these ratios are all 1. So you can flip it any way you want it. So first thing that you need to do is to learn how to think about a metric measurement and convert it to a couple simple ratios. Not difficult to do. Let's go ahead and look at one. Go ahead and write me 2 ratios to interconvert meters and picometers. Now step 1, you need to remember your prefixes. You know, the ones that we use commonly, they'll become so ingrained in your head that you don't need to really think about it. When you take an exam in my class, Everyone is allowed to bring one 3x5 card. Okay? And on that 3x5 card, you can write anything in the world you want. Now that's 3 inches by 5 inches, not 3 feet by 5 feet. Okay? That's the deal. But you can write anything you want. And if there are a couple of these that do follow you that you can't remember, write them very, very small in the corner somewhere, etc. But the ones that we use commonly, you'll just remember, I'm sure. All right, so we're dealing with picometers and meters. Pico is 10 to the minus 12, right? So we could say that 1 picometer is 10 to the minus 12 meters. That's a simple way to do it, isn't it? Or we could say that 10 to the 12 picometers would give us 1 meter. And we could write the 2 something like this. 1 picometer, remember the pico simply stands for this, is 10 to the minus 12 meters. 1 meter is the same as 10 to the 12 picometers. Let's do this again for meters and micrometers. Micro. Micro is, there we go, there it comes. This, it's the Greek symbol mu, and it stands for 10 to the minus 6. So go ahead and write a ratio for micrometers and meters. The first one is always really simple. All you have to say is 1 micrometer is 10 to the minus 6 meters. That's always your first one. And the second one, you simply change the exponent here such that you have 1 meter is 10 to the 6th of the micrometers. Think about the exponent math here. 10 to the 6th multiplied by 10 to the minus 6 is 1, isn't it? That's why we did exponents. All right, so here's how we write ratios. Well, let's do one more. It's so much fun. Do nanometers and meters. Nano. Nano is 10 to the minus 9. Well, if nano is 10 to the minus 9, then 1 meter is 10 to the minus 9, or 1 nanometer is 10 to the minus 9 meters, right? And then we simply reverse our exponent and say 10 to the 9th nanometers is the same as a meter. All right, why do we want to bother with all these ratio things? Because in reality, we do have to do conversions. Yes, we do. What we're going to do is learn a problem-solving algorithm here that is so universal that this is the only problem-solving algorithm you will need to get through this course, intro chem, general chem, and even organic. It is such a simple problem-solving algorithm. What it is called the give and find ratio method. We've just done ratios, haven't we? What you do is you look at your problem and you try to identify what's given. What's given in the problem, okay? Then you come up with a ratio that relates given and find. Very simple. If we were given some number in meters and we wanted to find kilometers, you would need a ratio that related kilometers and meters. Kilo's 1,000, and this is one of the ratios we could write. 1,000 meters is 1 kilometer. So let's do a real problem. I have 6,023 kilometers. How many meters is that? Well, what is given in this problem? 6,000 kilometers, isn't it? That's the number you're given. So you start off writing your given. We're going to multiply that by a ratio that's going to relate kilometers and meters. We can do that. There are two ratios we could write here. We could say that 1 kilometer is 1,000 meters, or 1,000 kilometers is a meter, or 1,000 meters is a kilometer, whatever. Right? Which ratio do you want to pick? What you do is you simply look at the two, and we're going to pick the one where the units of our given are in the denominator. The units of given must be in the denominator. Now, when we do our math, kilometers cancel, and then all we have to do is multiply 6,000 times 1,000, and we get 10 to the 6th meters. Now, in this class, I'm not going to do this to you, but in like general chemistry or so, it's always fashionable to do multiple ratios. So let's just see how we do that. It's not difficult at all. So what if the problem went all the way from millimeters to micrometers? Well, we would look at this and say, okay, this is our given, that's right. And we're going to need two ratios. One for millimeters and meters, and one for micrometers and meters. So we would write it out this way. Our given is our number in millimeters. We write that first. Our first ratio has to have millimeters in our denominator. So here I have 1,000 millimeters in 1 meter. That's upside down, isn't it? So I just have to flip it over. I can do that. Remember, I said I can flip these things upside down. When I do this, our millimeters are now set so that they cancel. And now, given as units of meters. So our next ratio must have meters in the denominator. So micrometer and meters in the right spot. Now we just simply cancel the meters and do our simple math. 10 to the minus 7 divided by 10 to the 3rd divided by 10 to the minus 6 is 10 to the minus 4. Now, one of the things that people have trouble with in doing these sorts of things is their own calculator. Everyone needs to have their own calculator. And you need to really be intimate with your calculator. You really need to know it, because every calculator is different in terms of how you enter all of these numbers and get the right answer. So before exams and stuff like that, do take a little bit of time, make sure you understand how to enter, multiply, and divide exponents on your particular calculator. Because if it's exam time and you say, I don't know how to do this calculation, I don't know either. I don't know how to use your calculator. They're all different. So take the time. There's a tutorial on this, so look at this, if you will, as another 5 points. This one is simply using conversion of masses. What we've all been raised here in the States with pounds and ounces and stuff like that. Silly measurement, but nonetheless, that's the way we live. These are just a couple ratios that you can work with. 1 pound is 454 grams. 1 pound is also 16 ounces. Here we have a fairly complicated problem. We're converting milligrams to pounds. Okay? It's a little more sophisticated than we did before. Step 1, our given here is going to be milligrams, isn't it? It's 100 or 1 million something milligrams. We have 10 to the 6 milligrams, and we need to find pounds. We need a ratio that's going to reflect milligrams to pounds. We know that 1 milligram, 1 gram is 1,000 milligrams, or a milligram is 10 to the minus 3 grams. Either one of those works. We also know that 454 grams is 1 pound because it says so right there. What we're going to do is use these ratios with this given and come up with our answer. Step 1. Here's our given. We take our ratio here. I flipped it over. I can do that, remember. So that my milligrams are going to cancel. And I'm going to get an answer in grams. Once I have my answer in grams, I'm going to use this ratio with grams in the denominator. I moved it down. Grams will cancel. There it goes. And all we do is multiply 1.38 times 10 to the third. Take that and divide it by 454. We get just about 3 pounds or so. Now this tutorial is a little more sophisticated than the other one. You do have to do conversions as you go. But the same deal holds here. If you do 5 or 10 of these and you get these correct, that's 5 more points towards your exam score. Let's go ahead and do one more in class here. Here we're converting simply grams to pounds, so that's just one ratio. Identify your given and write a ratio for me. Well, our given is clearly going to be our 3,000 grams here. Our ratio is going to be grams to pound. That's this guy. Our ratio grams to pound. This is our given. Simply multiply it. Grams is our given, so we have to flip this thing upside down. There we go. Now our grams will cancel. And we simply take 3,000 divided by 454. We're dealing with about 7 pounds or so. Any questions? Go ahead and try these. Again, if you click on the show answer, it will take you through the entire problem step by step. So it's a nice way to learn. Let's wind up the section just by doing some simple conversions here in class. Go ahead and take each of these measurements and convert them into the units that are shown here. Just in case you can't remember, kilo is 1,000, micro is 10 to the minus 6, nano is 10 to the minus 9, there's 1,000, milli is 10 to the minus 3. Or you could simply look back 2 or 3 slides and get the list.
Sorry, I think I left a book in here. Can I check?
I'm sorry?
I'm sorry, I think I left a book in here. Do you mind if I look?
Oh, okay.
Thank you.
See if you can find it.
Sorry, thank you.
No, what was it?
It was for my English. I mean, it's no big deal. I'll just go look in the cafeteria. Go.
All right. All right, we have 2,057 grams. We want to go to kilograms. We need a gram to kilogram ratio, don't we? The ratio we're going to use is this guy. 1 kilogram is 1,000 grams. I've set this up with grams in the denominator. Simply multiply these two things together, and you get 2.057 kilograms. Meters and micrometers. Micro, remember, is 10 to the minus 6. We want meter in our denominator. So the ratio we're going to write for this one could be something like this. Now remember, there are at least 2 ratios here that you could write that are fine, that are legal. You don't have to write the same one I do. As long as it's a proper ratio between these two with meter in the denominator, that works. All right, here's our ratio. Meter again is in our denominator. Simply multiply these out. Remember, we're dividing exponents to subtract, and we get about 10 to the minus 1 micrometer. Our next, we're relating grams and nanograms. Nano is 10 to the minus 9. Our ratio must have grams in the denominator. It would look something like this. Our exponents, we're dividing, so we're going to subtract our exponents. And this is 10 to the 5th nanograms. Meters and kilometers again. We've already done kilo, we know that's 1,000. We need meter in our denominator. We can do it with this one. Our exponents will subtract. and we get about 65 kilometers. Grams and milligrams, milli is 10 to the minus 3. We need a ratio with grams in our denominator. Grams will cancel. Our exponents, we're going to subtract, and we get 278 milligrams. Now we will revisit the given ratio method virtually at every stop that we make where we're working problems. This is our first time. You know, it's new to you. It'll be a little, what the heck's going on? But it'll get simpler and simpler as we do this. Any questions? One more thing that I'd like to talk about while we're on metric is temperature. There are 3 temperature scales. This is Fahrenheit. This is the one, again, that we're raised with. Freezing point of water, 32. Boiling at 212. Odd numbers. I have no idea where they came from. In science, we tend to use the centigrade scale. Centigrade scale freezes at 0 and boils at 100. Nice even numbers. That makes much more sense to me. There's one other scale that we will use when we do gas laws. This scale is actually anchored at what we will see is absolute 0. But the Kelvin scale is called. Our numbers go from 273 to 373, but conveniently there's 100 little degrees between these two, the same as centigrade. We'll do this when we do the gas laws, and again, the numbers here are odd because it's anchored at absolute 0, which is an interesting concept. But centigrade is what we're going to use most of the time. All right. Let's do a simple experiment here. What if I gave you a ruler and a little arrow, and I said your entire grade in this class depends on giving me the proper measurement for where that arrow is pointing? That would make it too easy, wouldn't it? Everyone can look at that and say, well, okay, I can do this. There's 50, 55, 54. It's more than 54, isn't it? It's not 55. What is it? Well, it's about 54.5. That looks about like that to me. If I was to say that it was 54, clearly that would be wrong. And if I said this was 54.6666667, that would be stupid, because there's no way you can tell what that is. The best guess you can get is that it's 54 and a half, about. This is the concept of significant figures. When we do significant figures, we're talking about a measurement. The last digit is our best guess. The others we're sure of. But the last digit is a guess. This is about 0.5. We would say that this number has 3 significant figures. 2 of them are real, we know them, and the last digit is always our best guess. In lab, when we do measurements, we will put down whatever. You're going to do measurements just like this, actually. You're going to put down whatever real numbers you have, and then you're going to do your best guess for the last digit. All right. If I give you a number and I ask you something like how many significant figures is in this number, what I'm really asking you is what's the certainty or uncertainty for a particular measurement? Okay? Zeros always give people problems. What you want to do is when you're looking at a measurement and you want to decide how many significant figures you're working with, you look first to see if you have a decimal point. If your number has a decimal point, any zeros in front of the real digits, forget about them. They're not real. If there are any zeros afterwards, yes, those are real. And if there are zeros in between real numbers, yes, those are real too. If your number does not have a decimal point, trailing zeros, here they're real. Without a decimal point, they're not real. And finally, just one more time, whenever you have a zero between real digits, those are significant. So it's not real tough to look at a number and say, here we have 3,400. Step one, do we have a decimal point? No. Therefore, trailing zeros are not significant. We have no decimal point. Trailing zeros are going to disappear. We would say that this measurement has two significant figures. So when we took this measurement, we were sure it was 3,000 and 400 was our best guess. Do we have a decimal point? Absolutely. Therefore, all of the leading zeros disappear. We have a trailing zero, but that's real. Therefore, this has two significant figures. We have a decimal point. All the leading zeros go away. Here's a zero, but it's between real digits, so it's real. We're left with three numbers. We have three significant figures. No decimal point. Trailing zeros go away. This is between two real numbers, three significant figures. Now that sounds hard. How about 6.02 times 10 to the 23rd? Well, let's do our exercise. If we have 10 to the 23rd, that means we're going to move our decimal here over 23 places. But the decimal point is implied, it's not real. So all of these guys are trailing zeros without a decimal, and they go away. We are left with three significant figures here, and we're left with a rule. Whenever you write a number, a measurement, in scientific notation, you put all of the significant figures out here in the coefficient. So if your measurement is good to 12 digits, I mean you really measure this down to 12 digits, you put all 12 of those in front, then put your exponent. Makes doing scientific notation very, very simple. Go ahead and convert these guys to scientific notation with the proper number of significant figures. 2 exercises in one. Oops, sorry. Our first number here, first we want to go to scientific notation. So we're going to put our decimal here. It's going to be a 10 to the minus 2. We have leading zeros. We know that those go away. So therefore we have 3 significant figures. And we would write it this way. Our next number. We have 4 digits. All of these will be significant, won't they? No zeros to mess with. Going to move it to the left 2 spots, positive exponent, but we put all of the significant figures in our number. Again, I pushed the button twice, I'm sorry. 93 million. These are trailing zeros, no decimal point, they all go away. 9.3 times 10 to the 7. Our next guy. We have a decimal point, so that means that when you did this measurement, that yeah, it really is 0.0. It really is. That's the number you measured. Was 0.0. That's your best guess. It was 0.0. Therefore, all of these are significant. So when we write it in scientific notation, we have to put all these guys down. Got to move our decimal 1, 2, 3, 4 places, and it should look like that. And finally, we have a decimal point and a bunch of leading zeros. We know that they all go away, don't they? Therefore, we have 3 significant figures. Our exponent here is going to be 1, 2, 3, 4, 5, 6. That's 10 to the minus 6. And it should look like that. Let's work these backwards. Just write these in decimal form with the proper number of significant figures shown. Our first one, we have a positive exponent. We're going to move it to the right 2 places. We have 3 significant figures, simply 257. 1.25, that's 3 significant figures. We need 6 zeros in front. 9.3, 2 significant figures, 10 to the minus 4, 3 zeros in front. This guy. This is 10 to the 4th, so we're going to move it 1, 2, 3, 4. Our decimal point will be here. These 2 are real measurements. And so they must show up here as 0.00. And finally, 278 times 10 to the minus 1, three significant figures, that's simply 0.278. Now, you know, you can put these things like this on exams and whatever, and that's boring. This is a much more, this is more fun. Here's a bunch of numbers. Arrange these in order of decreasing number of significant figures. This is actually an exam question that I gave at URC a few years ago. All right, mentally, you're just scanning these, and you're looking at them quickly, deciding how many significant figures there are in each one. Then all you have to do is arrange it. Well, in order to get the most significant figures, I would tend to pick out the ones with decimal points, because all those zeros will count, won't they? Here we have a decimal point. We have 1, 2, 3, 4, 5, 6, 7. Decimal point, so these are real. 1, 2, 3, 4, 5, 6, 7, 8. I think this guy's going to win. The next one then is going to be this guy here that had 7. Now, let's see. These are leading zeros. They go away, so that's only 2. These are between the 6 and the 1. Those are real, so this is going to be 5. No decimal point. Those are not real. I think this guy wins. Then we'd have to go to here. Got it. Let's see, this is going to be 2, this one is 3, no decimal. And by gosh, I got them right. Now, significant figures really are not difficult. Nonetheless, there is a simple tutorial, and it is worth 5 points to you. So far, we're up to 20 points on your first exam. How about that? How many significant figures in 58,100? Step 1, there is no decimal point, is there? Therefore, our trailing zeros are going to disappear. We're left with 3 significant figures. 12.722000. We have a decimal point, don't we? That means our trailing zeros are real. Everything here is real. That's 8 significant figures. Scientific notation, oh my gosh, how easy, because we remember the rule, don't we? In scientific notation, everything in your coefficient is significant. This is 4. And one more. We have a decimal point. Leading zeros don't count, trailing zero does. This is 2. Any questions? Once again, this will open up its little magic section down here and give you a chance to submit your name. All right, let's go ahead and stop with the math review, if you will. And let's go back and talk about matter, elements, compounds, and stuff like that. We did matter. We said matter was something that had mass, right? We said an element, simplest form of matter, only one type of atom. A compound results when we take two or more different elements and combine them. An example, this is a molecular model for methane. Methane is natural gas. It consists of one carbon atom and 4 hydrogen atoms. They're always bonded in exactly this arrangement. Every molecule of methane will look exactly like that. Methane, as a compound, would be a pure substance. Pure substance contains only one type of matter. It could be an element or a compound. It's not easily broken down. A mixture is simply taking 2 or more substances and putting them together. There are 2 types of mixtures we will deal with. One is heterogeneous. That's salt and pepper. Okay? We can see that. There's salt and there's pepper. Different things. Homogeneous mixture is something that's a little bit different. Here we have a true mixture, 2 or more substances, but they are dispersed such that every sample you take is exactly the same. A solution, if we dissolve sugar in water, every bit of your drink will have the same amount of sugar in it, statistically. Air is a mixture, a homogeneous mixture. So heterogeneous and homogeneous. This is a classic example of heterogeneous. This is gravel. Here I took a beaker, filled it with salt water. As it evaporated, the water went off or left with the salt. When it was all dissolved, that was a homogeneous mixture. All right, simple quiz here. We have a rock. Is a rock a pure substance? Well, you look at it and say, hey, it's pure rock. But a rock really isn't. If you take rock and you slice it, you can actually see that it's a heterogeneous mixture. It's just all squished together, just like our pebbles were. This is a thin section under a microscope, and again, you can see it is truly heterogeneous. These are gold bars. They all look different. All different size, different weight. Is this a pure substance or a mixture? Well, it is a pure substance because it doesn't matter what the shape of it is. These are contain only gold atoms. Only one type of substance in there. Kind of a trick question. Here I have ice and water. Is that a mixture? Yeah. I mean, we can separate that, can't we? We can go in there and take the ice out. Now it's all water. It is true, only one substance. But we have water in the solid phase and water in the liquid phase. 2 different. And therefore, this is, in fact, a mixture. Once it melts, it's a pure substance. But as long as we have ice and water, it's a heterogeneous mixture. These are crystals of table salt under a microscope. Again, they all look different. But table salt is the compound sodium chloride. It actually arranges itself in these little cubic crystalline arrays. That's why these are cubic. Only contains sodium and chlorine in an alternating array it is a pure substance. Look at this list and quickly decide: pure substance, heterogeneous, homogeneous, or an element. All right, air. We talked about air. I gave you the answer actually, right? Air is a homogeneous mixture of gases. Ground pepper, little flakes, big flakes, kind of white, kind of blackish, brown. Clearly, it's a heterogeneous mixture. Seawater, at least, within a little locality. If you go around the world, composition varies, but it is clearly salts dissolved in water. It is a homogeneous mixture. Sugar. Sugar is a compound. It actually looks like this. This is a molecular model of sucrose. That's our common table sugar. It consists of carbon atoms, hydrogen, and oxygen. There are 12 carbon atoms, 24 hydrogens, and 12 oxygens. Every molecule of sugar looks exactly the same. Gasoline. Gasoline actually starts off as petroleum, which is just one heck of a heavy mixture, and you boil off a fraction. You still have lots of different types of hydrocarbons in there. It is a solution of heptane, octane, etc. in a homogeneous mixture. And finally, gravel. We saw the picture of gravel. It is simply lots of little rocks. Any questions? Well, we talked about water melting to ice and stuff like that. That represents what's known as a physical property. The simplest physical property a substance can have is its physical state, whether it's solid, liquid, or gas. Physical properties we'll see are descriptive of a substance. Chemical properties we'll see are this little movie clip that I made is designed to do is to reflect what the particles are doing in solids, liquids, and gases. We'll go through each of these separately. This is designed to represent a solid. A solid is a lump. A solid will have certain shape and whatever. Liquid will take on the shape of its container, and a gas frantically bounces side to side everywhere. Phase changes. We can go from a solid. They have a definite shape, defined volume. Liquids, we have a defined volume, but they will take on whatever shape of the container they occupy, and gases just go anywhere that they want. If we take a solid, we can melt it and make a liquid. That's a phase change. That's a physical change. We can go backwards, of course, from a solid. We can freeze it. We can take a gas or a liquid. We can go to a gas, go back. We can actually go directly from a solid to a gas. That's called sublimation. All of these phase changes take place at defined temperatures. And these are unique for every substance. We'll see why. Because the things that define whether we're a solid, liquid, or a gas are unique to the substance itself. This is bromine. Bromine is an element. This Br2 is a diatomic element. This is a little vial that has solid bromine frozen down here. It melts. This is liquid bromine on top of the solid. And it's also very volatile, so it forms bromine gas. Bromine gas is extremely toxic. Don't do this at home. Bromine has a melting point of minus 7.2 centigrade and a boiling point of 58.8. All right, knowing that, if we're at minus 20, what's bromine doing? Well, the melting point is minus 7, isn't it? When you hit minus 7, it turns to a solid. If we're at minus 20, it's even colder than that, right? We are below the freezing point, and so it's a solid. If we take our little beaker of bromine up to 80 degrees, okay, bromine has a boiling point of 58. If we're at 80, we're above that, aren't we? Therefore, this is going to be in the gas phase. And finally, if we're at minus 0.12, I chose that number because everyone hates negative numbers. But bromine isn't going to freeze until we hit minus 7, is it? Not going to boil until we hit 58. Therefore, this is bromine as a liquid. All right. These are actually off an old exam also. Very simple question. Pure substance is 15 degrees above its boiling point is what? There are two ways that you can do this problem. You can either look at it and just know the answer. Or, if you're at all confused, you can generate kind of like a number line. Solid, liquid, and gas. Our phase change happens at the melting point and the boiling point, right? Our problem says we're 15 degrees above the boiling point. That's the boiling point. So we're here. Got to be a gas. Do another one here. Compound melts at 115, boils at 325. We're at room temperature, which is about 25. What is it? Well, let's do our number line again. Temperature line, whatever. Here's our melting point. Here's our boiling point. We are at 25, so that's less than this. There we are, and it is a solid. Another very simple one. With negative numbers, we melt at minus 45, boils at minus 4, we're at minus 36. All right, it melts at minus 45. It boils at, well, that's supposed to be minus 4, I'm sorry. And we're at minus 36. Well, that's simple. We're down here, we're below 0. So we got to be in the liquid area. Any questions? Very, very simple. Melting point, boiling point, the points at which we do changes. Now, why does this happen? I said that every compound, every substance has a unique melting point. Why do we have solids, liquids, and gases? It has to do with what are called intermolecular forces. Every particle in the universe has an attraction for every other particle. This isn't gravity we're talking about. It's just intermolecular forces at the atomic level. There is an attraction. So if we have a bunch of particles and we put them together, they're kind of like this. This is the little buckyballs that are so toxic to children. Well, that's a whole pile of them. And they're stuck together. This is a lump. If you imagine the magnetism being the intermolecular force here, this is what defines this as a solid with a defined shape, with a defined volume. This is the kinetic molecular theory that describes all of this. Basically, the KMT says that particles in a substance are always in motion. The only time that motion theoretically stops is absolute zero, and you can't ever get there. So things are always in motion. In a solid, all of these little particles are moving, but they don't have enough energy to break the force between their neighbor. So they just kind of sit there and they shake. This makes it a defined solid shape and volume. They can't get away. If we go to a liquid, if we take this and put in enough energy that we start breaking these bonds, then the particles have enough energy so they can slip and slide all over each other. But they can't break the force. They can move around, but they can't break it. That means the liquid still has a defined volume, but the shape is fluid. And finally, in a gas, we take our liquid and put in so much energy that we totally break all of the intermolecular forces, and these guys just fly in a straight line until they hit the container or each other. And that simply defines solid, liquid, and gas. The amount of energy you put in, particles absorb the energy, and you can start to break the intermolecular forces, and then finally overcome them. So, things that we want to remember. In a gas, particles have lots of energy. They're highly separated. Because there's so much room between them, you can compress them. That's how you can compress a gas. The attractive forces are totally gone. In a liquid, they're closely spaced. It's not compressible. It has a defined volume. You can't compress it anymore. They slip and slide over each other, so they take on the shape of their container. And finally, in a solid, attractive forces dominate. They keep the particles more or less in a fixed position, and they just sit there and vibrate. Those are the three things, or the three basic, or the set of basic ones. There's quite a bit left to do, actually, but when we left off, we were talking about properties. We did physical properties, talked a little bit about chemical properties, etc. Physical property that we did in our lab was density. So a day late here, let's go ahead and let's talk about density. Density is a very common physical property. It is essentially the mass of something. Typically, we're going to express it in grams, and we're going to divide that by the volume, typically in cubic centimeters. This is the cubic centimeter. A liter. A liter is a measurement that we will use for liquids in chemistry. A liter is 1,000 cubic centimeters. The abbreviation here is an uppercase L. 1/1000th of a liter is a milliliter, and that's 1 ml. 1 ml is exactly equal to 1 cubic centimeter, but you are exchanging. You can also express density using virtually any unit you want, as long as it's mass per unit volume. And make sure if you don't use grams per cubic centimeter, that you indicate clearly what units you have. For example here, if we had 1 cubic centimeter of gold, and we took its mass, it would be 19.3 grams. We could say the density of gold, quite simply, is going to be mass divided by volume. Our mass here is 19.3 grams. Our volume is 1 cubic centimeter. So we can say the density of gold is simply 19.3 grams per cubic centimeter. Very simple concept. Any questions? Here are some common things. Water, like I said, about 0.996 at room temperature. Quite often people say the density of water is 1. It's not 1 unless you happen to be at 4 degrees centigrade. Room temperature, it's a little bit less. Mercury. Mercury is very dense, 13.5 grams per cubic centimeter. You may have seen this. When I was a child, we used to play with it. It was so much fun. Taking coat a border with it and stuff like that, and rub it with your fingers. Today you can't because it's a neurotoxin. So, maybe that explains something about our entire generation. I don't know. Sulfur, about 2. Iron, about 7.8. Helium and oxygen are both gases. Now, because they're gases, they have very, very low densities. Quite often when you have something small like this, instead of showing it as 0.0001, whatever, you simply change your units and do grams per liter. So it's 1,000 times more. That's typically done for gases. Once again, it's valid as long as it's mass per unit volume. This is something that's kind of cute. Here's a guy, and he's standing in front of this giant puddle. It's a pool of mercury. And he's holding a cannonball. Now, if this movie works, and I hope it does, he's going to drop the cannonball into the mercury. There it goes. And the amazing thing is, it floats. Now, cannonballs don't float on very many things, do they? The reason, of course, is that here's the density of mercury, 13.5. Cannonball is iron at 7.8. So it's less dense. It's less dense. One will float on the other. Way back in, 1972, I think, National Geographic did an article on mining mercury and stuff like that. And they put in this picture of this worker. So here's a worker somewhere, and he's actually sitting on this big tub of mercury. Of course, his density is much less, so he floats. But like I said, sitting on mercury or even playing with it, it's not a great idea because it does emit very toxic vapors. They took this offline because they decided it was very, very tasteless, because the guy is clearly not quite with it. Here's a demonstration. This is something from the EPA. They were called in somewhere to clean up a mercury spill. It was in a home, actually. So you can't see it very well, but this is a carpet. And here's the wall. And in here, there are little teeny tiny dots of mercury. Somebody spilled something, okay? If you take this and shine a UV light on it, that's a black light, the mercury vapor will be absorbed by the black light, and you'll see a shadow. Shadow looks like this. So even though you can barely see little spots of mercury, see the vapor just streaming up here from it. So it really is quite toxic. As you might see, in the very large labs, they used to only use mercury thermometers, and there were little droplets of mercury everywhere. Everywhere. So it's something you don't want to mess with. Any questions on the concept? Let's go ahead and do a quick problem. We're dealing here with a gas. We have 250 cubic centimeters, and we see the mass is 0.45 grams. What we're looking for is the density. Now remember, density is mass per unit volume. We know the volume, 250 cubic centimeters, and we know the mass. So all we have to do is simply divide the two in order to get density. Here's our equation. Going to substitute in for mass, and we're going to substitute in for volume. We have 0.45 grams, 250 cubic centimeters. Simply do our division. Our density is 0.0018 grams per cubic centimeter. Mass per unit volume. Now, if you wanted to, you could move your decimal over here, multiply it by 1,000, and do this in terms of grams per liter. That's typically done for gases. In lab, we did not do the volume of an irregular solid. This is a very classic experiment, but this pretty much describes what we're doing. We have a rock. It has a mass of 43 grams, and we have a graduated cylinder here with 22.5 mils of water. We're going to drop it in. The rock will displace some water, and when it does, the volume increases to 45.6. With these data, you can calculate the density. The way this works is something like this. We're going to drop our rock in. When we do, we displace a volume of water that's equal to the volume of our rock. So to get the volume of the rock, what we're going to do is subtract the final and the initial. That gives you your volume. Now this actually is based on an interesting story. This is a painting of Archimedes many years ago. Turns out that the king was given a crown, and it was supposed to be pure gold. They suspected, however, that the goldsmith was crooked and that he had mixed silver in with it and kept the rest of the gold for himself. So they asked Archimedes to please figure out if this was pure gold or not. Well, it was very difficult because clearly you can't melt the king's new crown, can you? So, the story goes that he was reclining in his bathtub one day, and as he sat down, water ran over the edge. And it's because, of course, it was displacing the volume of the lower half of his body. And when that happened, he jumped out of the tub, yelled "Eureka!" and supposedly ran through the streets naked, saying, "I got it." So what he did was the same thing, just dropped the crown in, measured the change in volume, and determined that the goldsmith was indeed crooked, and of course they killed him. So this is what we're doing with our rock. Let's go back to our calculation. Again, we have mass divided by volume. Our mass is 43 grams, that's no problem. For our volume, we're going to take our final and our initial readings and simply subtract it. Remember, milliliters and cubic centimeters are the same thing. Do our subtraction. This thing has a volume of 23.1 mils. Do our division, and we get 1.86 grams per cubic centimeter. Also, you could write it as 1.86 grams per mil. I've shown this written a different way. This is slash centimeter cubed. Quite often you will see it written as a negative exponent. So centimeter to the -3 is the same thing as 1 over centimeter cubed. So milliliter -1, centimeter -3. Any questions? Well, I like doing problems. I hope you do too. We're dealing here with ethanol. Ethanol is grain alcohol, is the alcohol of consumption. It has a density of 0.79 grams per cubic centimeter. We have roughly half a shot of ethanol, pure ethanol. That's 15 milliliters, or 15 cubic centimeters. What is the mass of our sample? Now again, what we're going to do here is simply take and use our formula, except this time let's do our problem-solving algorithm. I think you'll see that this will actually make it simple. Our given here is clearly going to be our mass, 15 cubic centimeters. What are we going to use for a ratio? The ratio is our density, mass over volume. That's a ratio, isn't it? Our given, 15 cubic centimeters. Our ratio, 0.79 grams in 1 centimeter. And of course, we're trying to find the mass. That's the number of grams. Now remember, whenever you use this algorithm, you start off with your given. We're going to multiply it by the ratio, and the only rule you have to remember is that the units of given have to be in the denominator. This ratio, the way I've written it, grams per cubic centimeter, is right. So we can just stick it in. Of course, cubic centimeters will cancel. The only unit left here is gram, and that's what we're trying to find. So doesn't that work smoothly? Simply multiply 15 times 0.79, and you get 11.8 grams. Yeah.
But I would say 11.80, what is giving that?
Well, I have 3 digits here because if you think about significant figures, we have 4 significant figures here, but we only have 3 here. So you always want to go for the lowest number of significant figures. And that brings me to my next question. Is this correct? Because what about the 1? That would be 1 significant figure, wouldn't it? But remember, significant figures only apply to measurements. That's not a measurement, that's a definition. So 1 doesn't count, and we're dealing with 3 significant figures. Any questions? All right, let's go back to our friend Mercury. Its density is 13.5 grams per cubic centimeter. What volume is occupied by 999 grams of mercury? Our same basic equation here. It's mass per unit volume. We know the density, and we know the mass. What we're going to do is simply solve this using the formula for volume. There's our formula. Density, mass, divided by volume. Or volume is mass divided by density. Our mass here is 999 grams, and our density is 13.5 grams per cubic centimeter. Now, we have grams in the numerator and grams in our denominator, don't we? So they're going to cancel. And that leaves cubic centimeter in the denominator of the denominator. The thing to remember here is, since we're looking at 1 over 1 over cubic centimeters, that's the same thing as centimeters. So it's the reciprocal of a reciprocal. You're just flipping it upside down twice. And when you do that, it comes back to the top. So our cubic centimeter here is the same as moving cubic centimeter up to the top. And that gives us our volume measurement. So our calculation is simply 999 divided by 13.5, and that should give us about 73.7. Again, I use 3 digits because I have 3 digits in my mass. Now, in our exams and quizzes, I'm not going to require you to think much about significant figures, but be reasonable, okay? Clearly, you would not want to put 6 or 7 digits after this, because they're not real, okay? We could also solve the same problem this way, using our given ratio find algorithm. If we did this, our given is going to be our mass here. And once again, our ratio is simply going to be our density. So the players are these, 999 and 13.5 per centimeter. Why don't you take these, go ahead and set up the problem, and then I'll click the button and we'll look at it. given always comes first. Our ratio comes next. But uh-oh, this isn't right, is it? Because the ratio must have grams in our denominator. So what we do in this case is simply flip it upside down. That's better. Now we're set up so that grams will cancel. When they do, we're left only with cubic centimeters, which is what we're trying to find. Do our simple multiplication, division, and again we get 73.7. I think this is actually an easier way to do it, as long as you're comfortable with flipping your ratios here so that the units cancel. Once again, if you master this method, this simple algorithm will take you all the way through this course, 110, general chemistry, and organic. You won't need to do higher math than this until you hit something like physical chemistry. Very simple problem here. Liquid A has a density of 0.985. Liquid B has a density of 0.873. They don't mix like oil and water. Which liquid is going to float on the top? Think about our flow minor and is that of mercury, right? Less dense thing always floats to the top. Well, when we talk about liquids that do not mix, we use the term immiscible in chemistry. That means does not mix. Liquid B, the lower density, rises to the top. Any questions? Let's do another quick problem here. We need exactly 2 grams of acetone for an experiment. Now this is something that is real. I mean, this is the kind of stuff you do in labs. We'll be using acetone, that's nail polish remover. We were using that for do a reaction of something. You're going to need to know how much to add. Well, that's a math, isn't it? So here we need 2 grams of acetone. We can simply look up the density, it's 0.91. What volume do we need? Well, very simple. Let's go ahead and solve it with our algorithm. Our given is our mass, here's our ratio, and we need to find volume in cubic centimeters. Go ahead and set it up. We always start off with our given. We need to take our ratio and set it up so that the units are given are in the denominator. So we're going to have to take this guy and flip it over, aren't we? So that grams is in the denominator. When we do that, grams can cancel. Left only with cubic centimeters. Do our simple math. We need about 2.53 milliliters. Now, on your exams, you will have problems where you have to calculate density and stuff like that. Probably not a whole lot of them, but you will have some. What I always do after we do a concept is I go back to old exams and pull out half a dozen problems or so, so that you can see what a problem might look like on an exam. Some of these that we'll do are probably a little bit advanced for Chemistry 100, but they give you an idea of what it's going to look like. Go ahead and look at this. Think to yourself how you would solve it, and then we'll step through it. This is just like the problem we just did, isn't it? Because we're solving for volume, we know a mass, and we know a density. Let's just solve this with our equation. And here we're looking for the volume. Rearrange our equation. Here I've substituted in, here's our density, here's our mass. We need to move volume over. There you go. And now we simply do the calculation. 93 divided by 1.46, and it's 63.7. And by gosh, that's one of our choices. Now I have, well, I didn't in this one, did I? It's all cubic centimeters. A liter is 1,000 milliliters, so this is huge. This isn't 63.7 milliliters, which would be the same number. Look at another one. We have a volume, we have a density, and we're looking for the mass. If we did this with our algorithm, which I always think is simpler, here's our given, our 51.2 cubic centimeters, or mils. Here's our density, 1.45 over 1. Centimeters is in the bottom, and so it cancels. Now, if you don't like algorithms, you can do it the other way. Here we're looking for mass. We substitute in. We divide this in order to get our mass out. And again, we get 74.24 grams. Here we have a dilemma. Now, I would not do this to you on your test because I just promised that I wouldn't. But this is a significant figure thing. These are kind of like the same number here, aren't they? Except we're dealing with 3 digits here. This is 4. Therefore, we would want this one as the best answer. I won't do that to you, but I could. Let's skip this one because this involves unit conversions. Here we have kilogram per mil. The density we're shooting for, this is probably a little too much. Here I converted it. And did that. But I wouldn't do that one to you either. All right, I might do this one though. Here we have a density in kilograms per mil again. We're looking for a mass in milligrams. And we have 62.5 cubic centimeters. Again, we're looking for mass, just like the one we just did. Going to substitute in. Here's our density. Here is our volume. Now remember, milliliters and cubic centimeters are the same thing, so that works. Simply divide, and we get 0.0688 kilograms. Now, which of these is 0.0688 kilograms? Remember our simple density, our simple unit conversions. 1 kilogram is 1,000 grams, right? 1 gram has 1,000 milligrams. If we do our conversion here, this is the same as 68 grams. And remember, every gram has 1,000 milligrams, so 68,000 milligrams. The best answer here is going to be this one, because again, only 2 significant figures. Let's do one more here. Let's skip this one. Again, this is lots of conversions. This is what you are going to be really responsible for. This is yet another tutorial. This one is entitled Density 1. When you do 10 of these, you earn 5 more points. Isn't that nice? With this one, you simply have a table where you have a mass, a volume measurement, and a density measurement. What you have to do is figure out the missing value and type it in. And let's do this one first. We're looking for the density. That's going to be mass divided by volume. Going to be grams per cubic centimeter, so it's just a very simple division. 24.8 grams, 18 cubic centimeters. Do our division. This is 1.37. When you do these things online, remember, do not type in units or anything like that, because that will be wrong. Just type in numbers. Let's do another one and I'll hush. If our mass is this and our density is this, what is the volume? Density is mass divided by volume. Therefore, volume is mass divided by density. All we have to do is plug in our mass, 9396 grams, plug in our density, 1.87 grams per cubic centimeter, do the calculation, and our volume is 51.5. One more perturbation. Given these two, figure out mass. If density is mass divided by volume, then mass is density multiplied by volume. Substitute in, our mass is 0.621, our volume is 88. Multiply the two together, 54.7. Looks like there's just one more of these. Go ahead, we've done this one before, but solve for mass. Mass we recall is density multiplied by volume. Simply plug in your numbers, do the calculation, multiply these two together, and you have 25.8 grams. Now these are simple, and once again, if you have difficulty, you can, like it said, sorry, this is not correct. You can click on Show Answer. It will tell you what the correct answer is, and it will go step by step through the problem, explaining how you should have done it. This also has a view the section of the book. This is my book, and it'll bring up a PDF of the section from the book explaining it again if you just need to review. Remember, after you do 5 of them, the little magic thing enters, and you can submit it and get credit. Well, if there's a density 1, my gosh, there must be a density 2, right? Only makes sense. Density 2, instead of a table, we have a word problem. Yuck, right? Everyone hates word problems, but they're very simple. We're looking for a volume. We have so many kilograms of a substance, and our density is 95 milligrams, or 99,591 milligrams per cubic centimeter. Remember that these numbers come out strange like this sometimes because this is algorithmic. And every time you work this, you get a different problem. It makes up numbers as it goes along. So you will get a strange mix of units and whatever. To solve this, we're going to have to convert kilograms to grams, or milligrams to grams, so that we're working in the same unit. We have a mass in kilograms. That's the same as, remember that's 1,000, so that's 1.68 grams. Our density down here for some reason was given in milligrams. That's 1,000 milligrams in every gram. So that's the same as 9.5 for our density number. All we have to do is rearrange our equation. Volume is mass divided by density. And we got it right. Now this one's a little more sophisticated than the others, but it's still only worth 5 points. Nonetheless, at the end of the semester, if you don't do them, you're going to hate yourself. Let's just do one more here. We're looking for a density in grams per liter. We have a volume in cubic centimeters and a mass in kilograms. Again, we have to do conversions. We are given kilograms. That's the same as 3 grams. Here we have cubic centimeters. We want liters for some reason. So we have to divide this by 1,000. And now we just calculate our density. It should be about 8340 as the correct answer. Any questions? Go ahead and try these. All right. Let's go back to our discussion of other properties. We've done physical properties. We decided, that that's what something looks like, its density, state, color, all those things. Chemical property actually tells us how something reacts with something else. It's going to describe chemical reactions. When we do a change that is some sort of a physical thing like melting it, a change of state, called a physical change, is still the same substance. When we have a chemical reaction occurring, we call that a chemical change. and it will form new substances. So that's the test. This is kind of a cute reaction. This is aluminum. Actually, it's a little ball of aluminum foil. And this is bromine. We met bromine the other day. Remember, bromine is a brown liquid at room temperature, very high vapor pressure, so these are toxic bromine vapors. The tube has been sealed though. If we take bromine and aluminum, they're both pure substances, and we allow them to react, a chemical change will occur. This is the aluminum, and we're going to pour it into this fuming beaker of bromine. As we do this, the two come in contact, and they start reacting. Now you see light and heat is given off. This thing is just boiling over with toxic bromine vapors. And when it's all done, you'll note that there's this white crusty stuff around the edge and in the bottom. The white crusty stuff is aluminum bromide. It is a new substance. This represents a chemical change. We've gone from here to here, two substances, one substance, chemical change has occurred. This is what we will describe using a chemical reaction. Now in a chemical reaction, we're going to take reactants, in this case it's these guys, we're going to make a product, in this case aluminum bromide, and we connect the two with an arrow. Now in chemistry, the arrow has the same properties as an equal sign. So we must have the same numbers and types of things here and the same mass that we do over here. We'll talk about those concepts in just a little bit. Any questions, though, on the simple concept there? Here we have a shot from the winter time. Icicles. And you can't see this, of course, because it's static, but they are slowly melting and there's little droplets forming. It is still water, however, isn't it? Therefore, the process of this melting is a simple physical change. If, however, we took water and we put it in an apparatus like this and passed electric current through it, turns out that the electric current can split water. Water is made up of hydrogen and oxygen. When we run electric current through it, oxygen collects on one side, hydrogen collects on the other. We have made two new substances out of one. This is a chemical change. Any questions? Just look at this very simple assortment and decide if these are physical or chemical. We're forming frost again in the winter, I certainly hope not. Temperature drops on a winter night. Frost is made from water vapor going directly into a solid. Nonetheless, the ice crystals are still water, aren't they? That's the substance. Therefore, this is a simple physical change. In the summertime in Illinois, we can grow corn. Start off with the C. This is actually a very complicated process, isn't it? You think about the biochemistry involved. You take a little seed of corn, you set off reproduction, you make an entire stalk of new corns and stuff like that. This is a very, very complicated chemical process. Oops. We have a mixture of gases. Oh, no, a match ignites. And when it does, we're left with a little piece of ash, and we give off all sorts of gaseous stuff. We're making new substances, aren't we? Start off with a matchstick, wind up with carbon. We release gas as we do it. Again, this is a simple chemical process. You go out and you jog and you sweat. Yeah. But when you do that, eventually you dry. That's because the liquid on your skin evaporates, doesn't it? Started off as water, winds up as water vapor, simple physical change. And the last one no one knows about these days at all, because nobody uses silver forks. But if you did, if you had real silver, you would leave it out on the tabletop, and sure enough, it'll turn yucky black. Well, that's a chemical change. Turns out that there's enough hydrogen sulfide in the air to react with silver. When it does, it forms that yucky black stuff. That's a chemical change, of course. And that's why you have to polish silver to get it off. Silver forks and stuff like that are not in use very much anymore because they are, very high maintenance. Unfortunately, that means that we don't have a lot of silver. Every time that you use a silver utensil, something is real silver, a little bit of that silver dissolves with acidic food and whatever, and goes into your body. That might sound bad, but it's a good thing. Silver is actually a great natural antibiotic and just kills bacteria like mad. Back in the old days, only the upper crust could use silver. They could only afford it. And so the peasant population used lead instead. Lead forks. Problem with that is that same thing happens, except lead is a neurotoxin, and so you had this stupid population of peasants. All right. We talked about chemical equations. In a while, we're going to actually look at lots of these, we're going to learn how to balance them and stuff like that. But let's just look at some examples of chemical processes represented in chemical equations. Potassium is a solid. It's an element. It reacts with water. When it does, it forms potassium hydroxide and evolves hydrogen as a gas. The little letters you see here, SL, AQ, and G, stand for solid, liquid, gas, and AQ means aqueous solution, so it's dissolved in the water. If you look at this equation, on this side we have 2 potassiums, don't we? On this side we have 2 potassiums. We have 2 times 2, 4 hydrogens, 2 hydrogens, 3, 4, and we have 2 oxygens, 2 oxygens. So they have the same numbers and types of atoms on both sides. That's a very important concept in chemical processes. This is also a very fun reaction. This is potassium. typically stored under oil because it also reacts with the air. And this is water. What we're going to do is take a little bit and drop it in. Very carefully pull out a little chunk. And you see it reacts, obviously. It also burned. Did you note that? It reacted vigorously enough so that the hydrogen that you formed reacted with the oxygen in the air, and it burned to form water. This is the reaction that I just described. Hydrogen gas that's given off reacts with oxygen to form water. Again, do you count? 4 hydrogens, 2 oxygens, 2 oxygens. Same numbers and types of atoms. This is also a very fun experiment to do. This is a balloon. It's filled with hydrogen gas. And this is a lighter on the end of a long stick held by a brave person. Very much fun. Back in the old days, you could do things like that in class. That was lots of fun. But these days, they don't like you to do that. Any questions on the concept here? Decide if these are physical or chemical changes. In our first one here, we're taking a gold bar and we're hammering it out into a thin sheet of gold leaf. Gold, it turns out, is the most malleable of all metals. That means you can pound it thinner than anything else. You can pound gold so it's literally just a few atoms thick. It's amazing. Gold, it's called gold leaf. When you see like a dome of a church or something, it's white gold and it's real gold. There probably isn't more than a couple grams of gold in it because you can hammer it so thin and spread it over that it just, well, just goes forever. We start with gold, we wind up with gold leaf. It's the same thing. It's just a physical change. Here, we're taking water and we're boiling it. Starts off as water, ends up as water vapor, but it's still water. And if we burn a carbon bar or charcoal, in oxygen we get carbon dioxide, that's a new substance, and that's a chemical change. Look at some exam questions here. Which of these is a physical change? Well, lighting a match, clearly we start with a match and wind up with ash, right? That's chemical. If we put sugar in tea, we have sweet tea, but it's still sugar, isn't it? That's physical. Melting of aspirin. People are surprised to think of it this way, but aspirin is a real chemical compound. And yeah, it melts, but it's still aspirin. B and C are both correct answers. Carbon. Which of these are chemical properties? It's a solid. Chemical or physical? Well, it's physical, isn't it? Insoluble in water. Well, it just sits there. So that's just physical, isn't it? Soluble in carbon tet. Well, that's interesting, but it's still carbon. It's just dissolved in something. Reacts with oxygen. Well, that's a reaction. And crystallizes to form diamonds. Diamonds are nothing but pure carbon. Still carbon. Only D describes a chemical reaction. Which of the following statements is or are correct? Compounds cannot be decomposed into elements. Elements and compounds are pure substances. Well, that sounds right, doesn't it? Elements, but not compounds, are pure substances. I think that's silly. And now we have to say, is A and C correct or not? Well, if we said this is silly, it's got to be B. One of the other things that we could have done in the lab was to try to identify an unknown based on density. Now, since we hadn't done density yet, I didn't want to include that in your lab grade. So, this is the kind of thing that you would do, though. We have cadmium, copper, and zinc. They're all elements. And we have densities of 8.6, 8.9, and 7.1. We have a metal. We have a volume and a mass. What is the metal? Clearly, what we want to do here is calculate the density, right? And just compare it with unknown values. If we divide our mass by our volume, we get 8.92, which matches copper. We have a balloon with helium in it. The mass of that is 2.225 grams. And what's the volume? Our standard equation here has density equals mass divided by volume, so we solve for volume. Take the mass divided by the density, comes out to be 12,500 cubic centimeters. Remember, a cubic centimeter is the standardability milliliter, so divided by 1,000, we get 12.5 liters. Let's do one more. Most people just think of seawater as being salt water. It turns out that there's a huge amount of magnesium in it. There's also literally gold dissolved in seawater, lots of gold. But if we have seawater with a density of 1.03 grams, and we find that it has 1.41 grams of magnesium per kilogram, and we have 16.5 liters of seawater, how much magnesium do we have? Now, there are a lot of individual calculations here. I probably wouldn't put something this complicated on an exam. The mass of our seawater is 17 kilograms, okay? Multiply that by our density here, 1.41, 24 grams. Now that's an awful lot of magnesium, isn't it? Awful lot of magnesium in our seawater. Actually, seawater is used to as a source for magnesium and manganese. both elements. All right, let's end chapter